So, good afternoon, and welcome to the first technical session called Monitoring and Data Analytics in Support of Cyber Defense. My name is Mano Bihelgas, and I am a researcher at the NATO CCD COE, working in the area of monitoring and situation awareness. I'm also a third-year PhD student at Tallinn University of Technology, and my professional interests are mainly log analysis, data mining, and machine learning. But well, enough about me. And in general, the session handles making sense of both structured and unstructured data. When you think of it, how often do you have structured data that's giving you relevant security information, but usually it's the other way around. You need to analyze unstructured data to really get the relevant information necessary for you. While unstructured data might be more relevant, it's usually much more difficult to analyze it, especially with computers. Furthermore, the same raw data that you might be receiving will look and be prioritized differently based on the type of organization you're doing it for, be it private, military, or government, for example. However, in the end, it still boils down to finding the malicious actors that are trying to get into your network, and even worse, they might already be in your network. That's why we need to work on improving our monitoring capabilities, and that's what the session is about. But now, let me introduce the first speaker, Dr. Fabio Perazzi. Dr. Fabio Perazzi is a research assistant working on big data security analytics at the University of Modena and Reggio Emilia in Italy. In the same institute, he completed his master's degree in computer engineering and PhD in computer science under the supervision of Professor Michele Colaiani. During 2016, he spent 10 months as a visiting research scholar in the United States at the University of Maryland, working with Professor Submaramian on machine learning for malware classification and cyber deception. His research interests focus on security analytics applied to network security, intrusion detection, as well as malware classification, and in general on all solutions dealing with cybersecurity and analytics. The talk is titled Early Detection of Internal Cyber Threats. And let me also note that this is a proceedings paper, so you can also find the full article in the CyCon book. Thank you. The floor is yours.
Okay. I'm here to present the latest results of our research on detecting internal cyber threats. So, let me start with the question. What all these attacks have in common? In all of them, the attacker managed to bypass perimeter network defenses, and they remain undetected in the core of the network for a long period of time. Why? There are two main motivations. The first one is that we often focus too much on defending the perimeter of an organization, like with intrusion detection system, firewalls, or protecting some individuals with antivirus software. But once the attacker gets in, there are limited solutions for detecting whether it's actually within the network. And there are limited solutions for network behavioral analysis, in general anomaly detection, and for correlating multiple factors that may reveal its presence. There are several challenges to protect the network core. The first of them is, of course, the huge amount of data. We're talking about billions or millions of internal communications per day. One might think that most of the communications are between internal and external hosts, but also hosts within the organization exchange a lot of information. Another thing is that you cannot easily whitelist or blacklist a communication as legitimate or not, because it's not only client-server communication. There are a lot of legitimate client-to-client communications. Think, for example, about Dropbox, or in Windows environments, there are like a lot of broadcasting and file sharing protocols that can be actually useful for in a company, but that generate a lot of traffic, which is legitimate, but it's between clients. And also server often talk to other servers. Think about, for example, for DNS requests or backup. So you cannot easily whitelist any connection a priori as legitimate or not. And there is also a necessity for online processing, which means analyze the data, the traffic in real time as it arrives to perform early detection, because otherwise, like learning that our organization has been, that an attacker has been in our organization for 1 month is like not completely useless, but probably he has already brought big damage. And final challenge is like the risk of false alarms. Like, okay, we deploy an anomaly detection system, but if it generates too many false alarms, then the security analysts are just overwhelmed with inspecting stuff. And actually, they cannot provide any actionable countermeasures. So this is data from real data from the largest department of a large organization, and it represents the communication between internal hosts. Each node is a machine, and an edge exists whether two hosts communicated together. And this is just 1 hour data. And the DNS server is highlighted at the center just because most of those contact them, but you can see that the situation is kind of messy. And our goal is to find a needle in a haystack. Most likely, only a few hosts will be compromised by an attacker, and we need to find them and find them quickly. So there are 2 main drivers of our proposal. The first one is to perform multi-layer traffic analysis, which means not to look at network data from just one perspective, but look at multiple perspectives and correlate different events to improve accuracy in detecting the likelihood that an attacker is actually performing malicious activities. And the other main idea is to perform prioritization instead of detection. And that is because attacks are like black swan events, or, as I said, only few hosts may be compromised. So it's impossible in modern networks to be 100% sure whether that host is compromised, that host is not compromised. So the idea is to produce multiple indicators of risk for each internal host, and produce a final ranking to the security analysts so they can focus on the, say, top 10, top 20 most suspicious hosts that are likely involved in some kind of threat. This is a general overview of our approach. In input, we have from multiple sources. Multiple sources are collecting internal traffic data in the core switches of the network, and traffic data arrives as a stream. And then we have 2 main building blocks. One is for the multi-layer analysis, in which a first phase creates different representations from the network data, and where with representations, I mean, think about, for example, relations between hosts talking with different protocols, or representations of different network metrics like packets and bytes. For each of these representations, in parallel, an anomaly analysis is performed, which is then the input of the prioritization building block that correlates the anomaly outputs together to correlate different events and see whether one or more internal attacks are occurring. And finally, a risk score is computed for each host, and the prioritized list is given to the security analysts, which can actually focus only on the most suspicious one. So let me start talking about the first phase of the multi-layer analysis, which is layer modeling. We have traffic data coming in as a stream, and we create different representations that we call layers. Each layer is a graph. Different layers have the same internal host as nodes, but of course the edges are different. We represent different network metrics, packets, bytes, durations, and also layers for different protocols, like DNS, SSH, ARP requests, like more technical stuff. And then, for each of these representations, an analysis is performed in parallel for each internal host. The main idea here is that we have a current representation of the state of the system, and we compare it with the behavior in the recent past. So we compare for each layer and for each internal host the current state with respect to the past, and implicitly with respect to the other host, because this module extracts metric from the layer, which, of course, represents relations between internal hosts. From this, a set of anomaly indicators are produced, but these are just the anomaly indicators of that particular layer. For example, think about just the generic layer representing just who is talking with whom at the network level, of course. If you can detect some anomalies there, but it does not, I mean, by itself, it does not mean anything, because it must be correlated with some other event, because otherwise it can be just maybe a machine installed a new software and started some broadcasting activity, which is not necessarily malicious. So if we just look at one layer and try to say if an attack is occurring from that one layer, it's not sufficient. The outputs of the analysis, so for each layer, we have multiple anomaly indicators, and they are correlated to see whether one or multiple attacks are occurring. In particular, we focus on internal cyber threats, so on attacks that might be going on in the network once the attacker gets in. For example, he may try to perform reconnaissance to move to find new hosts to compromise and get closer to its target, or transfer data to an intermediate drop zone before actually exfiltrating it. Or there is like also the watering hole attack, in which the attacker shows like fake websites to the other employees to trick them into putting in their credentials, or can use it also to compromise their hosts. Also by correlating the outputs of the layers, also other kind of attacks can be defined. In this presentation, I want to focus on two of the most interesting attacks, which are man-in-the-middle lateral movement. So what is man-in-the-middle? It's kind of a surprisingly easy, and I mean, once the attacker is within the network, has compromised the first host, it's kind of easy for him to intercept all the communications of the other host within the same LAN. And what he can do is eavesdrop and even forge requests that pass between the victim and any other host. So all the traffic of the victim passes through a host controlled by the attacker without actually leaving any evident trace at the IP level on which most of the network security appliances work. because it's actually working at a lower level of the TCP/IP stack. But the idea is that we managed to prioritize this kind of activity by correlating events from different layers. The strongest indicator is an increase in the packets and bytes activity, and this is because, as I showed in the previous slide, all the traffic passes basically through the switch twice. So even if the source and destinations remain the same, all the packets are duplicated because they pass through the attacker. Here I reported 2 time series extracted from the packets layer and the bytes layer on 2 days. On day 1, the man in the middle was not occurring. On day 2, the man in the middle was actually occurring, and the packets are more than duplicated. From the multi-layer analysis, a state change is detected in both these layers. However, these 2 indicators are not sufficient by themselves, because they might just represent an increased activity, like an increased network activity of a host. So to reduce the chance of false alarms and increase confidence, we have to correlate this also with a stable number of contacted hosts, which is an information extracted from another layer. And also there is a more technical thing about the IP MAC correspondences from the ARP layer. By using these 4 indicators, we are able to prioritize man-in-the-middle activities performed through ARP spoofing. Another example is lateral movement, which actually is a strategy for me. Usually the attacker, once he gets in the network, he did not compromise its final target. He just tries probably the easiest way to get in, maybe through some spear phishing email. But once he is in, and he needs, if his target is within a restricted area of the network, he has to compromise multiple hosts. And since maybe he cannot access that area from the external, he will need to create a common propagation tunnel. And this activity in particular is called pivoting, and there have been many attacks in the past 3 years using this type of technique. And I want to give you an intuition of how this can be detected through the layer analysis. The idea is that here we have, on the left side, I have 2 graphs. I've reported 2 graphs which are like the communication between 6 hosts. On the top, there is the like a baseline representation of who talked with who in the past week. And in the current state, I have a new edge, saying that there is a new communication between 4 and 5. Just keep in mind that, again, it's also other characteristics are important. It's not just the edge itself, maybe it's also the duration of the communication. But from these 2 graphs, we can build reachability graphs, which are like represent which host can be reached by whom. So for example, in the first graph, we have that host 1 can reach 2, 3, and 4, but then in the current state, it can reach also 5 and 6, and 4 can reach 5 and 6. So this kind of analysis can be a strong indicator of lateral movement activities. So finally, we are in the prioritization model. We have computed for different types of attacks for each host. We have correlated the anomaly analysis on the different network representations. We combine for each host the attack risk scores. And the intuition here is that if an attacker has compromised, I mean, even if he compromises one of your hosts, he may be performing more than one of these activities at the same time. So by combining them, we can get an overall threat score, because for a host, he might be performing like some reconnaissance, moving some data, then trying to perform some pivoting, or man in the middle. And The idea is that the final output is a prioritized list of hosts given to the security analysts so that they can focus just on the top K hosts instead of like analyzing all the thousands of them or inspecting individual events. And they can also analyze, starting from the highest host, they can then inspect which risk scores were high and why that host has been classified in a high position. These are just some results. You can find the full results for different types of attacks in the paper, but we basically injected different man-in-the-middle and lateral movement activities, and this table on different classes of internal hosts. And this table reports the percentage of time in which the attacker has been prioritized within the top 5 or top 10. And we can see that basically for both attack, especially for lateral movement, more than 96% of the cases it has been prioritized in top 5, and for man in the middle, in more than 95% of the cases it has been prioritized in top 10. And in our data set we had 1,012 hosts. So you can see that it can be very helpful, like to isolate which hosts should be inspected. In conclusion, I would like to say that protecting large networks has become increasingly challenging because attackers have become more sophisticated, networks become more complex, more logs are generated, and security analysts are overwhelmed. And here we presented a novel approach to defend the core of an organization. And first of all, we decided to focus on internal network data, communication between internal hosts. And in particular, we focus on net flow data, which is a summarized representation of network used for processing speed. And then an online analysis of, we propose to do an online analysis of anomalies that is required to provide timely detection, because otherwise for offline post-mortem analysis is still useful but cannot prevent real damage. And we propose to consider multiple representations of the data, of the network data, and correlate anomaly events to increase confidence that an attack is occurring. And finally, we'll propose to consider prioritization instead of certain detection, which is not realistic anymore certain detection is not realistic anymore for modern advanced cyber attacks. That's all. If you have any questions, I'll be glad to take them. Thank you.
Any questions? Wait for the mics. Just
no, wait. I didn't hear.
Yeah.
The information that you gained, was it any of it dealing with?
I'm sorry. Who is talking?
Right here, over here, in the back.
Oh, okay. Yeah.
Is any information that you gained by detecting the information and then injecting yourself into the communication in order to falsify a victim, or and gleaning that information into how you can define attack vector or C2, and then possibly also seeing where your information is and how the attacker is compromising your network?
I'm sorry, you are asking?
The information, have you allowed yourself like a honeypot or a victim to be injecting itself into the attacker's network to see what they're doing, like attack vector or C2? Is any of that information that you provided actually allowing itself to show that you have notified like the communication with the attacker, and then analyzing your own network to see how your communications have been compromised?
So we simulated, for example, for the man-in-the-middle activities, we perform controlled experiments, but on the real network data by performing actual man-in-the-middle, which does not require any compromission of hosts.
It's all simulation.
What?
All of it was simulation, is my question.
I mean, it's done on real. I mean, it was a real experiment done on real data. But for the lateral movement, it was in part a simulation, but we did it in a virtualized environment and injected it on the real data, on real hosts. So it was the traffic generated for by the lateral movement activity was injected in the metadata of the traffic of real internal hosts.
And from that, hello, sorry. And from that information, you did recursive analysis to decide or determine how many hosts had been affected because of the communication, or?
I mean, we were looking, I mean, since the experiment was controlled, we knew where we placed the attacker, and by applying our algorithm, we were looking whether in the top 10 or top 20, our the attacker host was prioritized.
Do you have any other questions? There.
Hello, Lieutenant Commander Joe Hatfield, U.S. Naval Academy. I actually had two questions. They were basically clarifications. In your model, I found it quite interesting that you were able to essentially run algorithms at 2 layers. So you had sort of like link layer analysis and you had network layer analysis. So my first question, just for clarification, you're looking for signals versus noise. Is a signal that you identify at a link layer going to inform your prioritization at another layer, or do they stay at that layer for the prioritization of the potential attack? And then the second question has to do with your baseline. And is that a fixed baseline, or is there some way you can have that be moving with time so that new information, new behavior, and then if that's the case, how do you account for drift in data where something that was potentially normal is now not normal activity, or usually the other way around, right? So you have something that's not normal, but now it's become normal, and now you're getting all these false positives.
Okay. Yeah. So about the first question, if I understand correctly, I mean, we have an online processing constraint here. So for all the layers in a first step, the analysis is performed independently. So I don't know if that was the question, if like one layer can feedback another layer. But in the beginning, I mean, in the first phase, all layers are processed independently. But then all the outputs are analyzed and correlated by the other module to see whether there are changes in, it's like a post-correlation. Anomalies are detected in each layer, and then there is a second module that takes these indicators. For example, if an anomaly occurred, it's also the intensity of the anomaly. There are like other data. I just gave it a simple representation, but in the first step, all the layers are performed independently, and this is because of performance reason, because if they start feedbacking each other, it's not possible. And as far as the second question is concerned, you're right. I mean, in this example, I just put a fixed baseline just to give an idea, but actually in traditional time series analysis also, there is a lot of techniques for adaptive time windows. So what you can do is, I mean, we applied an online state change detection taken from actually another paper. You can find a citation, or I can give it to you if you want. But the idea is that there is, you're analyzing a time window, but you keep track of, for example, the mean of the data. if the mean deviates too much, you change the baseline, and you can adapt also, the length is usually adapted with respect to variance of the data. But anyway, there are many statistical solutions that can help you to provide the adaptive window. And this can be done because for the layer analysis, basically it's only a statistical analysis. Then for the attack analysis, the outputs of the layer are examined. So I don't know if that replies to the question or.
Okay, thank you. If you have more questions, then I would kindly ask you to take it later up after the session, and but would you kindly join me in thanking the speaker again?
Thank you.
Okay, so up to our final speaker. So the topic is exploring how cognitive computing can help to bolster cybersecurity, and Dr. Andrea Melegari has also prepared us a live demo, and he is a Chief Marketing and Innovation Officer at CyForgate. He is focused on intelligence and security solutions for businesses and government agencies. Andrea has gained extensive experience in coordinating projects that employ complex technologies to support strategic analysis of data. He holds a degree in computer science and is a member of the board of directors for CyForgate and also Expert System both in Italy and the United States. If you're ready?
Ready.
Ready.
Okay.
Go ahead.
Okay, so thank you for this opportunity and thank you in advance for your attention. Just a few slides in order to present the live demo that I will offer you. So, we have to consider that the next malware generation will be more dangerous. So cyber criminals are planning to use all the most innovative software technology to create the best virus. So we have to consider that in the future, we have to face robots, not exactly hackers, or better, hackers that will use artificial intelligence technology. And we must do the same, right? But for facing this new scenario, it's very important to consider that we have two different types of data. We have unstructured data, and you know very well what I mean when I say structured data, but we have unstructured data. And the structured data are so important because inside unstructured data, you can find intelligence. So what is the goal? The goal is to make sense of structured and unstructured data. When I talk about unstructured data, I consider FireEye reports, papers from researchers, news about the cyber domain, and so on. So a lot of information that we use just for a little portion of their value. What is the problem? The problem is that dealing with unstructured data is very hard because when you have a text, you have to read the text, you have to understand what is the topic of the text, you have to extract entities, you have to connect entities, and something else. So it's very, very difficult. And also, if you have legions of analysts, it's not so easy. So, what about cognitive computing? Cognitive computing means the possibility to develop software that can mimic the way of our human brain. Before going through the live demo, take a look at this very funny example. This is a real situation, obviously we are stressing how is difficult to analyze a text. So this is a very interesting example where we play with 3 different meanings of buffalo: the city, the verb, and the bison. So imagine our problem in understanding this kind of situation where, again, we are dealing with a grammatically correct sentence. By the way, in the bottom part of the slide, you can find what means buffalo, 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 buffalo. Okay, so this slide, in order to anticipate you that cognitive computer is a very good technology, but it is not a perfect technology. Probably will not be a perfect technology for this reason. In the next 10 minutes, 15 minutes, I will offer you a live demo of this cognitive computing solution. So let's go live. First of all, consider that it's something that you can test. So it's something that you can test using www.intelligenceapi.com. So it is available, and clicking on live demo, you can immediately go through the live demo environment. So I love to risk, and I love to analyze with you something completely new. So go to the Google News. This is the Google News page. Let's try to find out something which is related to our domain. Let's consider the first content. This is the document that could contain interesting intelligence for us. Okay, it's a very long document. You need a lot of time to understand the documents, to extract people's relationship, and so on. So take a look. We copy the URL. We go back to the live demo. Here. We paste the URL here, and then we crawl the document. So the first result is what you get with this preview. It is a sort of summary of the metadata that the cognitive computing has processed. So, first of all, one of the most interesting aspects here is to understand the content of the documents. So, what you can see here in the left column is the list of the topics that the Cogito technology discovered. We have organized the content of the left column in different sections. The first section is dedicated to the intelligence taxonomy. So we are talking about 1,000 different categories. Then you have a crime taxonomy. Then if we scroll down, we have terrorist taxonomy, geographic taxonomy, and cybercrime. This is very important because a cognitive computing solution must deal with text using different point of view. If you are in the intelligence domain, probably you are interested in the first results. If you are part of the law enforcement agency, probably crime taxonomy is what fits for you. And if you are a cyber analyst, probably the result coming from the cyber taxonomy will be what you will deal with. It's very interesting that when we click on a topic, we highlight the specific portion of the documents where the topic is mentioned. Take a look. In the first yellow sentence, you don't find arrest, the keyword arrest, okay? Again, if we click on another topics, you understand that the categorization derives from a semantic elaboration. Okay, so it's very important to understand that the documents is related to our domain, and it is also very important to quickly highlight the portion of intelligence you have to take a look. And again, here you can click in different, on different topics, and you can get different results. So the capability to analyze a document and to determine if the document matches one of the topics of your interest is very important. Because imagine you gather millions of documents and you have immediately to understand what are the documents that are important for you. Second option, when we extract the document, we are interested in extracting entities. So in the left column, you will find different kinds of entities. You will find not only the traditional entities, people, organization, places, but also other entities that could be very important for you. So if you are, I don't know, involved in protected infrastructure, here we are saying, oh, there is an embassy. If you are involved in the cyber defense, this document talks about cyber attacks. And at the same time, when you click, you highlight, okay? So this is very important. So if you select one people, the system highlights not only the proper name, but also the role, lawyer. And if we scroll down, oh, good, she. If you cannot deal with anaphors, you miss a lot of information. Andrea Melegari works for Expert System, period. Today, he is in Tallinn. If you don't solve he, and if you don't connect he with Andrea Melegari, you miss the relationship between Andrea Melegari and Tallinn. One of the other functions that you can find in this demo is what we define semantic reasoning. So if the documents contains Donald Trump, we are talking about United States, important person, chief of state, and so on. If in the document we find FBI, we are considering a bureau, and so on. Or we can extract events. What is an event? An event is a specific situation where you can find something correlated with other entities. So in this example again, what you can see here is that coming back to the topic of this symposium, we found cyber attacks, and we found, I don't know, FBI. Again, we send you back only the specific part of the document where FBI is mentioned in a context that is related to event we have highlighted. So here you have the possibility to identify not simply a topic, but a topic that involves Andrea Melegari or FBI. Emotions. It's not so simple to deal with emotions. We can categorize, we can identify more than 80 different emotions. And it's very important that exactly in the same way I showed you before, you can select the specific emotion and you can identify specifically the emotion where the entity selected is mentioned. We try also to put the events on a timeline. It is not so easy because sometimes you have absolute time reference, for example, in 2014, but sometimes you find relative on 7th of February. So you can separate old situation, recent, present, and future. The capability to analyze the document considering entities and the relationships is something that you can use here. The graph that you can see here now is a graph that describes Nikulin relationships. Zoom in this graph, and it's very interesting. I found funny things. Finally, Nikulin is linked with Lamborghini. Why? If we scroll down, I think, oh, here you can find the relation with Lamborghini and another relation with Lamborghinis. Take a look, Lamborghinis, plural, and another one here. When we select relationships, we can also classify the type of relationship. Here, the relationship between Nikulin and Lamborghini is economic relationship. Why? Because the verb is buy. So not simply a connection between Lamborghini and Nikulin, but we can classify the relationships. You can do the same also if you select facts. So if you select facts, you can highlight all the diagrams that connect our guys with other guys. And in the same way, you can see the specific part of the knowledge where you can find the facts that you find in the graphs. You can do the same for organizations and for places, obviously. The last function I would like to share with you is the write print function. Very important. Sometimes you deal with text, but you don't know the author of the text. Imagine if you have to monitor social media. You will find Mickey Mouse, the account Mickey Mouse. It could be very useful to use this technology to gather important information about the style of the writer. Here, in the left part of the screen, you can see 65 different linguistic parameters that we have calculated. We can also extract the verb classes, the verb tenses, the slang, and finally, the readability index and the vocabulary richness. This is very important for understanding the goal of the author. We use a lot this function in order to understand where there is proselytizing on the network, okay? Or where you can find disinformation. At the end, on the right, you can see the write print. It is the biological information that you can use to compare this text with other text. Coming back to the demo, it's very important that when you consider this kind of technology, you should have something that can work in different situations. Now we have selected a different content, Kabul bombing, kill, and so on. At the same time, you can select and you can put your URL here, and then you can, oh, sorry, the test is too long. Anyway, we can select another content, but it's very important to stress that we can manage different contexts, giving different results. So, just to recap, what is the goal of my presentation? So, we have now a technology that we can use for creating knowledge from unstructured data. So we have a huge amount of unstructured text. We have the cognitive computing technology, and we can use this technology to build a knowledge base. When we have a knowledge base, we can use the knowledge base. If you get a new content on the left, you can immediately map the main important semantic metadata, and using this knowledge DB, it's very easy to compare what you can process now on the left with the content of your DB. And then you decide what you have to do. This is a real example of technologies that many customers in Europe and in the US are using. We have invested a lot of money and a lot of time in develop this kind of technology. And again, if you don't consider that Holy Grail exists, this kind of technology could offer you a very interesting support for dealing with your data. That's all.
Thank you. Do you have any questions from the audience? There.
Thank you. The natural language text processing has been in the focus of AI last 30, 35 years. So, and I see here many interesting points that you made. My question is, I understand that you are not really dealing with a, let's say, standard language, but you are dealing with kind of domain-specific languages like medical text or security text. Because if you deal with a standard language, you have to take account not only the one things that you see on the screen, but the computer, the cognitive computing, has to do a lot of, has to have a lot of information about the history, social background, common sense, such kind of idioms which are specific to, let's say, tribal life or specific to life in New York. So, do you count such kind of language expressions like idioms, anaphoric expressions? How much you take count of context? Do you use, what you showed here is a semantic graph for this Mr. Nikulin. But how much it differs, for example, with conceptual graphs by John Sova, or frames and so on, which multiple representations already have been done in AI.
Good question. You're right. What I show you today is the solution we have developed for this domain. We have different APIs for different domains. For example, Cogito Intelligence API is the API we have developed for the intelligence domain, but we have Cogito Finance API, we have Cogito Oil and Gas API, we have another API for dealing with social text, which is a completely different thing. When you deal with the social text, we have to completely rethink our grammar analysis. The people that write inside social text don't follow grammar rules. So we have modified the grammar analysis and the logical analysis. So the question is very correct. This kind of technology works if you customize the ontology, the taxonomy, the linguistic analysis to the specific domain. In this specific situation, you can increase the quality in terms of precision and recall. But the technology we have is a general technology. For example, if you take a look at the customers we have, Zurich Insurance, we have government, we have banks, we have oil and gas company, and so on. So our capability is to analyze also general English, okay? If we want to get the best precision for a specific domain, obviously, we have to customize, we have to train the system with a specific ontology. So I have to speak with you, I don't know, about biologic problem, I don't know nothing, so I have to read a book in order to discuss with you properly. At the same time, this technology is something that you can customize for your specific need. And in this way, you can increase the quality. In our experience, when we customize the technology, we can get from 85% to 95% of quality in the disambiguation. Okay? 100% doesn't exist. But 90% is pretty good. Sorry, we don't develop graph. So the graph that I show you is just an example of what you can do when you get the relationships between entities.
Another question?
Yes, just a short one. Not every bad guy speaks English. So what about different languages or even a mix of languages?
We have developed this technology for 12 languages. Some languages are very good because we have a lot of customers. Other languages is something that we are developing now. For example, now we are developing simplified Chinese, Russian, and Korean. We know what we have to do. What we need is money and time.
And actually, what about mix of languages? I know that other companies really struggle with this.
It's really a problem because when you have documents where you can find sentences in different languages, our approach is splitting and creating different texts for the different languages, but it's very hard. Again, you can do very interesting things. Other applications are so difficult.
Okay, thank you.
We have time for one more question.
Yeah, sir, thank you for this excellent presentation. What I was wondering, is the tool also able to correlate various sources, because single source information doesn't give you facts. So I was wondering if it's able to correlate, because for a tool like this, when you enter text, then the old rule, garbage in, garbage out, will apply. So is it able to connect different sources and then give this kind of information?
Yeah, in this specific example, you have seen the process of one document. Here is the implementation we have realized for DoD, US DoD, with Google. We are partnered with Google, and this is an example where you have many texts, and when, for example, you search, you get the context, the traditional list of documents in the center of the document, but every document is also associated to the topics, and here you can use this in order to filter the document, many documents, for different goals. So you can combine and you can insert this technology inside an existing system. We did it for Google, Palantir, SharePoint, HP Autonomy, and so on.
Okay. Thank you.
Thank you.
Here's a small gift for you as well.
Grazie. Thank you.